Okay, hello everyone. Welcome to a working session for our physics project. So we have a bunch of topics here because I don't think Jonathan and I have done these live streams for a little while. And so we have a lot of pent-up supply of topics. The one that we're really going to dig into is local multi-way systems. But of course, I have a distractive initial topic that I wanted to bring up, which is, so I've been thinking about quantum mechanics and the analog of Lorentz transformations. Maybe we shouldn't do this. Maybe we should just go to local multi-way systems. I think that might be a better thing. Let's not distract. We'll get way off track if we do that. No. Now Jonathan's ready for a distraction. Okay, that's okay. So the issue is this: if you have the question is, what's the analog of a Lorentz transformation in branchial space? And is there a way to set up something which is kind of like an inertial frame? And so what I was thinking is, if you have a quantum circuit that's just a bunch of wires and they are connected like you would do for a transposition sort, where the wires are just in this kind of grid of connections. And then you ask the question, if you, I mean, I don't quite know how to formulate this, but if you're looking at, you have input on the left and output on the right, is there how would you normally, given that quantum circuit, how would you normally think about it computing something?
Is that a rhetorical question, or?
No, that was a question for you, because I
mean, if you have a tensor product initial state of qubits or qubits, right, and each element of the tensor product goes into one of the wires and comes out the other side. I mean, that's.
Yes, but what's the timing story? I mean, you're basically multiplying by a bunch of matrices, right?
Right. Which is why circuits come in layers. So, for instance, quantum circuit operator has layering built in the.
But so how should I think about? I mean, in terms of time, there is, those unitary operators can be constructed presumably from Hamiltonians and represent the elapsing of a certain amount of time. Every layer is a certain amount of time. Is that correct, or is that not correct?
Well, you can think of it that way, but the whole point of a circuit representation, rather than say an annealing representation or something, is so that you only have to deal with discrete time. You don't have to care about time evolution operators or something, because the point is each layer is a discrete time step.
Fair enough. But so in other words, if I'm going to say, let's do a Lorentz transformation and let's change the relative timing of the different parts of each layer, that you're claiming that's sort of a nonsense thing to do in the circuit representation.
Well, it requires reformulating what the circuit representation is, right? I mean, okay, well, to make this concrete, right? So like if we have a circuit represented in Wolfram language, it comes in layers, right? And the layers are telling you the timing information.
Right, but so we go from left to right, and we're saying the successive vertical column, the successive horizontal columns there correspond to successive quotes moments in time, right?
Right. So in the naive version of a the naive version of a Lorentz transformation that you're discussing, you would have to deal with situations where, for instance, this S gate and its control qubit are like the input for the S gate and the input for the control are ingested at different times, and then it's kind of not clear how you deal with the outcome of that computation. Now, as I say, there is a self-consistent way to think about Lorentz transformations on quantum circuits, but it requires what I was talking about earlier.
Which is what?
Well, it requires essentially not modding out your representation by the conformal group.
But so imagine we had a lot of wires here, right? Then it would be the case if I simply were to look at, we could just have, you could make one, like 20 wires, okay? Then the notion of a maximum entanglement speed does have imagine we take the limit of the number of wires going to infinity, okay? So that then we can think about Lorentz transformations again as something which is initially discrete, but then limits to a continuum. So I mean, if I'm not mistaken, if we have enough wires, it will be the case that that we have some kind of entanglement cone that we can see within the, even with these discrete time steps, we can see the entanglement cone build up across the wires. Is that a true statement?
Well, not in the circuit picture, because in the circuit picture, you say you have effectively modded out by the conformal group. There is no space-like structure here. Of course, physically, there is there are bounds from things like, there's the Margolis-Levitin bound and other kind of bounds on, how quickly information can propagate in a quantum circuit, but those aren't dealt with in the circuit picture. You need something.
But I'm confused by that. I mean, when you say it's not dealt with, I mean, if I have n wires, where n is a large number, I do know which wire has, I have some basis, and I know what the amplitude is for a particular qubit to exist on a particular wire, don't I? And therefore, I would surely know if I started off with something where all qubits, they're all 0 qubits. I have some state in which everything is a 0 qubit, and then I start poking the circuit somewhere. Most wires will still have 0 qubits after some number of rounds of some number of layers of the circuit, just because they haven't yet had a chance to interact with the wire that didn't have the 0 qubit. Am I confused?
But that depends on the structure of the circuit.
No, I know, but assume that the circuit.
The only thing related, the only thing close to a geometry on the circuit is the gate set. Exactly.
The geometry is defined by the structure of the gates. So imagine that what we did was something like a transposition sort, where basically what you're doing is every pair of wires, every adjacent pair of wires is connected. For example, a trivial example would be you have something where an even odd transposition sort type thing. I mean, not that we're doing sorting here particularly, but we're just saying we put a gate that does something. I don't know, is there an exchange type gate that does something on pairs of wires? Right, so it's a kind of checkerboard of connections between wires.
Yeah.
Would that not define, I mean, that would implicitly define a geometry for this system, wouldn't it?
Well, in the sense that you'd have an undirected graph. You'd be looking at essentially the evolution of information on an undirected graph.
Okay, but I mean, that would mean that there's
nothing quantum about this. I mean, you could do the same thing with a Boolean circuit.
Well, except that you could do that for a quantum circuit. You could do that tracing quantum amplitudes, couldn't you? With that circuit. What's that?
Or with a Boolean circuit. This whole thing can be done with Boolean functions. There's nothing about what you've just said involves quantum mechanics.
Well, it depends what the gates actually do. If the gates are just swapping, then presumably that can be, all they're doing is.
Swap gates are. I mean, that's a classical operation. There's no.
I understand that. But if we have some kind of thing which changes, I don't know, in the ZX calculus setup, for example, aren't there sort of elementary gates that, well, I forget that. I mean, there's a certain set of, you can get, I mean, obviously we can have universal quantum gates that can get to any quantum amplitude by just having something which has some rotation or something like that in it. But I'm not sure that really matters, because what I'm curious about is just whether
the fact that a quantum gate is a gate set is universal does not mean that you can get to any amplitude. Any more than knowing that a cellular automaton is universal tells you you can get every possible register configuration. That's not what universality means.
Fair enough. Okay. Well, anyway, the thing that, okay, maybe we can.
I mean, my view is that there's a very, very concrete way of thinking about this, which doesn't involve circuits. It just involves multiway systems, right?
Go for it. And maybe it's actually a segue to our second topic about Gokul multiway systems, because maybe it's actually related to that. But tell me what.
The point is that in all notions of quantum computation that we generally think about, like circuit models, there's an idea that you have synchronization across all eigenstates that appear in your superpositions, right? Mm-hmm. So if we take a multi-way representation of a quantum gate, or the evolution of some quantum circuit, let me look. Okay, here's an example. then, we are always assuming effectively a cosmological rest frame, in the sense that we assume everything that's on the, all the eigenstates that appear on the 0 time step appear in the same superposition. All the eigenstates on the 1 time step appear in the same superposition, etc. If you relax that condition, so you now generalize the notion of superposition, so you can have eigenstates with different that are not strictly synchronized, then that lets you capture the exact analog of conformal transformations.
Okay, fine. This is consistent with what I was talking about, but I'm confused about why it could not be actualized in a quantum circuit. But I get.
But you would need to generalize the notion of a quantum circuit in the way that I described earlier. You'd have to not mod out by the conformal group.
Okay, explain to me why, when you talk about, okay, so here we can take different reference frames for looking at this. I mean, if we take the example, a trivial sort of example of a grid multiway system, we could see how different, we can pick different reference frames if they're just sort of parallel, if they're just sort of straight slices. We can just pick ones which are differently boosted, and they will have a different set of states considered to be the, quote, simultaneous states, aka the states combined in superpositions. Right.
So we're talking about two different levels of thing, right? So there are relativistic transformations that occur at the level of the superpositions, and there are relativistic transformations that occur at the level of the tensor products. So, and it's not, you can't just deal with one, which is what you were discussing with the circuit example, right? With relativistic transformation of circuits, when you're just looking at effectively desynchronizing what happens on each wire, you're doing relativistic transformations of tensor products of the qubits, but you're not relativistically transforming the actual eigenstates that appear in the superpositions for those qubits. And that's not mathematically consistent. You need to transform both.
Okay, let me walk through that again, because that was too fast for me. So what are you saying here? So you're saying that one thing you could do is, we got this multiway system. Imagine it's a grid multiway system. We've got all kinds of, at each stage relative to the cosmological rest frame, we have a certain set of states, which are of quantum eigenstates, which are going to be combined in a superposition. Is that the right setup?
Yes. I mean, what I'm saying is really very simple. So in this multiway system here, there's only one qubit, right? It's a two-level system. You can see that each state vector is a two.
Okay.
Right. So there's no tensor product here. So in the circuit representation, this has only one wire. But there's the point is, this is still relativistically transforming, because you're constructing some arbitrary, there are multiple ways of constructing antichains in this multiway system.
Okay, so the point that you're making, which by the way is deeply connected to the global multiway system business, I think, is that there is one, as soon as you add more qubits, you've got, you're tensor producting up those states. And so you're in general going to have 2 to the n. Why are there, I don't quite understand, why isn't a qubit, what exactly is going on here? What is this thing?
So this is showing a superposition of eigenstates.
Okay, so there's two, wait a second. So explain what we've got, no, I don't understand what's happening here. We've got 2 eigenstates and each one has a quantum amplitude.
Right. So, but in this particular case, to simplify things, we treat the imaginary and negative directions as being distinct, which of course in reality you wouldn't, but to treat that in full generality requires a coordinatization theorem on branchial space that we don't yet have.
Okay, but so this is a discretization of the quantum amplitude represented as a pair of numbers. I don't quite understand that. So yeah, so what's going on here?
Graph, one step, let's say, includes state pathways. Vertex labels, vertex weights. Yeah.
Okay, all right. That might be simple enough for me to understand. Okay, so what's going on here?
Oh, sorry, let me. basis. Let's start with a. Oh no, actually that's fine. We can do 1 plus I and 1 minus I as our initial state, something like that. Okay, so we've got 1 plus I, 1 minus I. That's our initial state. So you can see we've got a 1, 0, an I, 0, a 0, 1, and a 0 minus I, and they're each weighted 1.
So
right?
Wait a minute. So those are representations of quantum eigenstates, each with magnitude 1.
Right.
And the phase is not yet being defined. Is that correct?
Well, I mean, this is why we have. So in reality, of course, you just have 1, 0, and 0, 1. If there were a general way of extracting phase from branchial coordinates, because we don't yet have a general coordinatization on branchial space, we can't do that. So I'm baking in the phase by also treating I0 and 0 minus I, etc., as being eigenstates as well, which of course is unphysical.
Okay, so by baking in the phase, you mean what we actually think determines the phase is, in a sense, position in branchial space. But here, instead of having a representation of position, you're putting in the actual name of the state. You're putting something which describes its phase. Is that right?
In effect, yes. I mean, so what's actually happening is I'm defining all possible, all possible orthogonal directions in this Hilbert space as being separate eigenstates. And then, so then all the multiway system is doing is just shifting around weights between those vectors.
Okay, but so the positions, the branchial positions, the relative branchial positions of the states that you get after 3 or 4 steps, what is the significance of those relative to their quantum phase? In other words,
well, of course, in the physical case, that is their quantum phase. There is a 1-to-1 correspondence between their branchial coordinate and their phase.
I understand, but for example, this thing I did recently about multiway systems with numbers, okay? So I looked there at this question of if you actually put numbers on the nodes, basically, and then you use those numbers as a coordinate system, there's a reasonable question, which I did look at, of what is the correspondence between the branchial coordinate system, the implied branchial coordinate system, and the explicit numerical coordinate system. Did that make sense?
Yes, I understand the problem.
And there was some vague correspondence in some cases, but okay. But so here, what we're doing is we're approximating the implied coordinates of branchial space by burnt-in coordinates of the actual numbers, so to speak. That's right?
Yes.
Okay. So then the point you're making is that there is one sense of making a Lorentz transformation which will be relative to that either genuine branchial space or implied branchial space, so to speak, or your burnt-in numerically determined branchial, numerically determined coordinates. Is that right? So you could imagine just doing Lorentz transformation with respect to your numerically determined coordinates, which might not be an accurate representation of branchial space, but it might be some approximation. Is that right?
No, what I'm saying is that I'm stating the consistency theorem that I was able to prove for this case, which is that you have to have the tensor product Lorentz transformations and the eigenstate Lorentz transformations covary if you want to have a mathematically consistent theory.
So this is what when you say tensor, so I mean, if I took this thing here and what you've got here, and I added another qubit, so instead of having vectors with 2 elements, I have vectors with 4 elements. Is that correct? Mm-hmm. So then, but then what's the other, so that will then become much more complicated, right? Yes. Okay. 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 So no, wait a minute. What happened there? So that is how did you make, I don't understand, what's the operator here?
But the thing called operator.
Well, I realize that, but what is its significance?
Oh, this is, I think this is a square root swap or something. It's something
Okay.
like that.
But when you took that Kronecker product, you're taking the product, you're saying independently on each wire, do a square root swap. Is that right?
Yep.
That's what the Kronecker product means. And
Yep.
so then you've got two things here. You've got a Kronecker product on the original description of the qubits, and then you've also got a Kronecker product in the operator. Is that right?
Yep.
And the point that you're making is that in order to get a consistent thing, you have to have you have to make transformations both on the state and on the operator. Is that right?
No, the point I'm making is, so you were talking about quantum circuits and relativistic transformations on the wires of those circuits. Those are Lorentz transformations or conformal transformations that are applied at the level of the tensor product. But
Yes.
within qubit that's being, or qubit that's being tensor producted, there are eigenstates, and those also relativistically transform. And it's not good enough to only transform one and not the other. You have to, they are covariant quantities. You can't just treat one.
Okay. No, I can see that. I mean, look, the thing that I'm wondering is, I mean, the thing that got me sort of piqued my interest here was the possibility there might actually be a physical experiment one could do to measure maximum entanglement speed. That it might be a physical experiment that effectively involves something with a large number of quantum wires. Is that conceivable? So, I mean, the maximum entanglement speed has the consequence, does it not, that it should have the consequence that there are degrees of freedom that get affected only slowly, so to speak.
Yep.
And it's a little confusing to me that, well, I guess I'm confused in a sense in traditional quantum mechanics. If I just have a bunch of wires or a spin chain for that matter, there is the Hamiltonian determines how quickly information spreads across the spin chain. But we're imagining that there is a kind of a lowest level Hamiltonian which describes how the information spreads. Yeah, all right, this is a complicated story. Well, right. Okay, go ahead.
It's kind of clear what the prediction is, right? It's that that you have a quantum circuit that's described by a tensor product of qubits, and a tensor whose initial state is described by a tensor product of qubits, and whose circuit is described by a tensor product of wires. And then you just say, well, I can compute an entanglement entropy for any pair of wires, and the prediction would be that information propagation is higher. It takes longer between wires that have higher entanglement entropy. And that.
Well, I mean, which is to say, when there's a higher density of stuff in branchial space, it takes longer to hop because there's more hops you have to make in branchial space, which is not what you would necessarily have thought about if you didn't believe in a discrete underlying setup.
Sure.
Because without a discrete underlying setup, there's no reason for it to take longer, is there, to hop between different parts of branchial space. Is that a true statement? In other words, in a traditional setup with traditional continuum quantum mechanics, you would not expect, unlike with physical space, where we readily believe that there's a maximum speed of light, that there is no such similar thing, is there, in ordinary quantum mechanics? Or am I mistaken?
Well, not in quantum mechanics, no. In quantum gravity, there is, or is conjectured to be. We've discussed.
Right, but I mean, okay, but quantum gravity has space-time, stuck in it as well. Whereas what we've got is a thing like that, but without any space-time. We've got a branchial. Go ahead.
No, but quantum gravity certain conjectures in quantum gravity, in particular, as we've discussed, the ER equals EPR conjecture, imply that that there should exist this effect in quantum mechanics because the corresponding effect exists in space-time.
I get it. I get it. I understand that. But then at a concrete level, the question is there a way of actually making a quantum experiment that could measure this? And in which, what does one expect to have happen if one has, and maybe this is too, you have a bunch of essentially quantum wires, and they're connected by various quantum gates. And, what is the normal expectation for, I suppose it's just the ordinary quantum Hamiltonian determines how quickly the amplitude builds up in wires, in distant wires. I'm trying to understand the difference between what happens in our setup and what happens in traditional quantum mechanics, where you're basically just looking at propagation of a lump of amplitude, so to speak, through different connections according to some Hamiltonian.
Mm-hmm.
Is it obvious what the difference is between that setup, that quotes classical quantum setup, so to speak, and what we have?
Yes.
Okay. And what is that? What is the difference?
Well, it's the difference I just described. So you in the conventional quantum mechanical setup, the notion of discrete wires, the notion that you have a discrete set of of operators or of qubits or qudits that you're tensor producting together is thought to be an approximation, right? And when one actually constructs quantum circuits experimentally, you are trying to set up a continuous quantum system in such a way that it approximates this discrete one, that
Yes.
as can, right? And so, in particular, in the true quantum mechanical picture that's being dealt with in an experimental quantum computing setup, the notion that you could compute an entanglement entropy between a pair of tensor products as qudits doesn't really exist, because those are thought to be a fiction, whereas in a discrete setup they do. That's the
Well, right. The measurement of entropy in a setup where everything is continuous and there's no counting of information is a tough business. Is that what you're saying, or something different?
Well, yeah.
Well, okay. So I'm just trying to understand. Is there an easy way to say what is the?
It's just like what you see. I don't know. It's like the classic Sorkin calculation of entanglement entropies for black holes, right? The first step in that is say, let's assume that we can discretize spacetime, so we basically treat the causal structure of spacetime as being a collection of coupled harmonic oscillators, and then we do the entanglement entropy calculation for those harmonic oscillators. If your picture is continuous, then anything that involves discrete computations, including computations of entanglement entropies, is necessarily an approximation. If your picture is discrete, then of course it's not. I don't see why.
Right, but I guess what I'm asking is it obvious to you if somebody actually had a great big quantum lab that allowed them to set up, arbitrarily complicated quantum circuits, is there a measurement that you could suggest that they do that would measure maximum entanglement speed? What is the analog of the Fizeau toothed wheel or something for measuring the speed of light for this case?
I don't have any refinements on what I already proposed.
So say again what you proposed.
Just construct a quantum circuit.
Yeah.
Measure the entanglement entropy between different pairs of wires.
How do you do that in an actual circuit?
Well, you would design the circuit in such a way that the different pairs of wires have calculable entanglement entropies.
Even though, as we say, to calculate it requires a discretization of some kind.
Yeah, sure, but
okay. And then the question would be, as you increase the entanglement entropy, does it increase the amount of time it takes for certain quantum effects to propagate? Is that, that the theory?
Yep.
And then the notion would be, as you increase the entanglement entropy, that you should sort of see a linear increase in the amount of of time to propagate the quantum effect somehow.
I don't know about linear, but certainly monotonic.
Right. Well, somebody should do it. Okay. Maybe we should change topics here and go to what we originally thought we were going to talk about, which is local multiway systems. And I think you have some lovely functions now for doing local multiway systems. So maybe you could bring those up and we could just take a look at what
Sure. So a bunch of them have been submitted to the function repository, although they only got submitted yesterday, so they haven't obviously been approved yet. So like the ones that have been documented are things like string local multiway systems, which maybe are the easiest to understand. I don't know.
All right, let's start there.
Okay, so here's the basic idea. We have, Stephen, do you have a favorite string multiway system?
Let's see. The one I've been using is what the heck is it? It's A goes to AB. No, I don't know. I have to look it up.
Okay,
I hope you have.
A goes to AB. It's a fairly boring one, but we can use that.
No. That one is way too boring. There's some. Let's pick one. Hold on. I have a favorite one. This is the problem. Whenever people ask me, like even for cellular automata, that's why it's good to have numbers, because I can remember the numbers. I can't necessarily remember the bit path.
Actually, boring might be good to begin with, just because it'll be easier to decode.
Yes, that's a good scheme.
Okay. More exciting. Okay. So if I now do string local multiway system with the same inputs, same rules. Okay, here's what I get.
Can you make that window wider?
Oh yeah, sure. Sorry, I was, of course.
Okay, so let's go back to let's go first to the traditional multiway system.
Right. Okay. So with a traditional multiway system, your states are global and your events are global. Right. So your state contains the whole state of your abstract rewriting system, and the event ingests the whole state of the abstract rewriting system and outputs the whole state of the abstract rewriting system. If you right, that's what we're seeing here. With a local multiway system, everything is kind of decomposed. So you have local tokens and local events. Local multiway systems were my attempt, because my personal philosophical prejudice is that it makes sense to treat tokens as local, but events as global. Because the reason for that is that the events are the things that effectively assemble the tokens together into global states. And so if you want to be able to do things like isomorphism testing and a non-trivial state deduplication, it makes sense to have the events be global. But it also makes sense to have the tokens be local, so you don't have to store the whole state of the system at every possible time, at every different time step. So that's what a local multiway system is doing.
So let's try to understand this. So what was the initial state is AA.
The initial state is AA. So let me explain what's going on. So here you can see we've got one token as the initial state, A. Now that token is being ingested, 2 copies of that token are being ingested into this event, because the input for this event is AA. Then
how does that token know that there are 2 of it, or does it not know?
It doesn't know.
It's a deduplicated token where, as far as it's concerned, it's the only one.
We'll come back to that. So token deduplication is a slightly subtle thing. But okay, so there are 2 copies. The point is that there isn't any notion of like the notion that tokens are a bounded resource is a notion that is respected by the events rather than respected by the tokens, if that makes sense. Okay. This event knows to only ingest 2 copies of A. It's not that A itself knows that there are only 2 copies of itself.
Yep.
Okay, so it ingests 2 copies of A and it outputs 2 copies of A and 1 copy of B, because the output is ABA. So then we got these 2 tokens here.
How does it know the order of the output? It doesn't from the tokens.
It doesn't just from the tokens, just like in a local multiway system. Again, it's the events that care about the order. It's not the tokens.
Mm-hmm.
So the default case is that everything is deduplicated. Everything is not deduplicated, but we can say deduplicate tokens goes to true. And then we get something that becomes a bit harder to analyze. It's a lot more compact, but it becomes much harder to analyze. So here you can see now, rather than having copies of A's and B's for every possible output and input, we've now just got 1 copy of each token at each time step. But the number of evolution edges becomes sort of unfeasibly large quite quickly.
Okay, so in a purely local multiway system with essentially a token event graph, what would happen here is that event, here I'm not actually seeing any multi-events. right? I mean, in this particular system, I don't think this is any different from a token event graph, is it?
I mean, in the sense that the system is confluent, yes.
No, I mean that those events, if those events were...
you mean there's no, right.
No, there is a difference. There is a difference. I see the difference. The difference is the spectators are included in the events here, whereas the spectators are not included in the events in a token event graph.
Right, exactly, because the events are global. So the point is that unlike with a token event graph, it's so the thing that there are several things that I like about global multiway systems. One of them is that it's trivial from this to reconstruct both the purely local token event graph and the purely global, evolution causal graph. Like somehow both of, information about both of them is encoded in this one object.
Why do you need the tokens? Why do you need to have tokens here? To be able to do that reconstruction? Is that obvious?
Well, you need to know how many copies of each thing were ingested and output.
But you can read that off from the event, can't you?
Yeah, but that's like saying you don't need an evolution causal graph. You can just reconstruct the whole thing from the causal graph. I mean, that's also true.
Right, but which is ultimately true, although in both cases, there's a question of reference frame.
Mm-hmm. Right, which also gets kind of exciting.
What's that?
Which also gets kind of exciting.
Okay, well, so I'm just trying to understand this. So the main difference here is that the events include their spectators, whereas in a token event graph, they do not. Mm-hmm. In a token event graph, they only include what actually was ingested and changed. Here they include basically spectator tokens that are just that just have a null event happening to them, that are just copied, correct?
Right, exactly.
Okay. And what you do, so in the next step, you are deduplicating tokens. Mm-hmm. And that means that, okay, so let me understand this. But you're not deduplicating across time steps. You're only deduplicating within a given time step.
If I deduplicated across time steps, it would become essentially structureless. I mean, it would basically just become a causal graph.
Is it, or is it a Petri net of some kind?
It would be a Petri net if the tokens had, some kind of resource limitation semantics. It would become something like a Petri net.
Right, but I mean, but am I not mistaken? Am I mistaken in thinking that one way to view the evolution of a Petri net is that you have certain, as they call them, tokens, but we have to call them something different because they're not the same as our tokens. Some kind of markers that, indeed. Right?
I might. Wait, make Petri net.
Let's look at a Petri.
This might be the incomplete function repository function. Yeah. Okay. There we go. Here's a multi-way Petri net.
It's very swank. Okay, so let's understand. So there, how should I understand this in terms of the thing on the underneath? Maybe it's not worth understanding that, but I mean, the main point is that in a different foliation, your choice of deduplication will be different. Is that correct? For the thing underneath?
Yes, right, exactly.
But your claim is that because the events are global, there's a unique sort of bipartite layering, in some sense, of events and tokens. Is that correct?
Mm-hmm. Yep, indeed.
So how would I make a different foliation of this whole thing? What I would be doing is saying there are a different set of events that I claim are simultaneous events.
Yeah, exactly. So it's the same as making foliations of just space-time. And in fact, that plays it. Okay, let me show you something else. If I take this thing, run that. Okay, so let's take this and just show its branchial space. So this is what a branchial graph looks like, a glocal branchial graph. So this contains information both about, okay, so you'll notice there are essentially three different kinds of edges here. There are token to token, token to event, and event to event. The token to token and token to event edges are colored in purple, and the event to event edges are colored in orange for reasons that will become clear in a moment. So effectively, this is encoding both evolution ancestry, because, okay, an ordinary branchial graph, like for something like this, just encodes evolution
ancestry.
Right. So it's saying these two have a common ancestor one step back in the evolution graph or in the state graph. A glocal branchial graph encodes evolution ancestry of the same kind. So when you have a pair of tokens that are connected, like, you know, these two.
Noting that these are non-deduplicated tokens.
Non-deduplicated, exactly.
If they were duplicated, that would crush the branchial graph to practically nothing.
Yeah, so in the deduplicated case, it's a bit less interesting. But anyway, let me show the.
Okay, there's still causal structure, but there's no state structure.
Exactly. So when you have a pair of tokens that are connected by a branchial edge, that means that they have a common evolution ancestor. Same when you have a token and an event. It's saying that this token was spawned by this event. Then when you have two events and they're connected by not by a branchial edge, but by a causal edge, that's telling you that they have shared causal ancestry. So these two events share a causal ancestor.
Sorry, let me come back to something for just 1 second here. So I mean, in the purple, so the structure of this thing is sort of a bipartite layered thing. So every token has as its ancestor an event.
Yes, exactly.
Right. So to say that to connect two tokens by a purple edge is to say that those two tokens have a common ancestral event. Is that correct?
No, that they have a common ancestral token.
Okay, but in that picture there, you've got over on the right, for example, you've got an event, and that event clearly connects to the tokens A and B because those tokens are generated by that event. A goes to AB, generates an A token and a B token, right?
Yes, exactly.
So two of those edges, the two edges coming,
Yeah. So the events to token edges are telling you this token spawns this, this event spawns this token.
Yep.
Token to token edges are telling you these tokens have a shared evolution ancestor. Just like in a regular branchial graph, having a shared state ancestor.
I understand, but then that means that, so can you show the actual evolution event graph for this thing for a second?
Oh yeah, sure, sorry.
That was A goes to AB, and we can look at...
You mean the glocal case or the multiway case?
The glocal case.
Okay.
Okay, so let's look at that thing over on the right. A goes to AB, and then there's a BBB at the... I think it is... Where is it? Oh yeah, it's over. It's the fourth from the right. Can you just highlight the fourth thing from the right? That one there, isn't it?
Yeah.
Okay. All right. So now those AB tokens are precisely the ones that show up with many. I see. Oh no, this is very, very confusing. That those AB tokens, there's just one of them in that evolution event graph. But am I seeing multiple copies of those A's and B's in the branchial graph?
No, you're seeing their ancestors.
Why are there ancestors there? I thought we'd moved on to a new generation of tokens here. I mean, why are the ancestors there? I thought the branchial graph was just recording the ancestral relationship between the A and B. Why are there multiple A's and B's there?
Which A and B are you talking about? You mean the two A's and the two B's that are connected to this thing here?
Yes, that's what I mean. Why are there two A's and B's connected to that event? Why is it not just one A and B?
Okay. So sorry. So in that case, it's because there are two A's and two B's that are relevant in the output here to common evolution ancestry one level back. There's one spectator B that's left off.
Okay, I'm sorry, you have to try that again. Well, in a normal branch hill graph, I would expect that though the AB that comes out of that event, comes out of the A goes to AB, BBB, spectator event, that the A and B that come out of that event, oh, I see what you're saying. You're saying that their common token ancestry includes the AB that are somewhat to their right, coming from the other event.
Exactly.
Okay, so there's actually two levels of this kind of branch hill graph that you could draw. You could draw a branch hill graph that purely includes the event to token piece, right, without including the token to token piece. And what's that?
That's true.
Okay.
So the reason for wanting to choose this specification was that unlike global branch hill graphs, this specification gives you all the information needed to reconstruct the full evolution causal graph if you know just the sequence of branch-like hypersurfaces, which you wouldn't otherwise be able to do.
Sorry, it gives you enough information. So normally you would have enough information to reconstruct the multi-way graph, but not the causal graph, right?
That's correct. You could reconstruct the states graph, but not the evolution causal graph. This global multi-way branch hill graph gives you enough information to reconstruct both.
Okay, and you were about to explain the event-to-event edges there.
Right. And so the event-to-event edges are telling you that there's shared causal ancestry. So in addition to, maybe it's easier to see on one of these things. So in addition to, we normally think about branch pairs as being state branch pairs, right? So like ABA goes to ABBA.
And we considered the other case. We considered causal branch pairs, but we thought they were trivial.
Right. Yeah, it turns out that they're not trivial. And the way that you can see that they're not trivial is by looking at these. But yeah, so in effect, these are telling you causal branch pairs, if you like.
What happens if you just take the multi-way causal graph and look at its branch hill graph? And we did try that, I remember. Maybe we had bad luck in what examples we tried.
No, I mean, when you have global states as well, it becomes less interesting. I mean, like you can, I think it's called just branch, is it event branch hill graph? I forget. Yeah, it's kind of dull.
Well, no, I'm not convinced it's always dull. Explain why it's dull. We had an argument back a year and a half ago for why it was dull, but it wasn't totally convincing. And now you're telling me it actually isn't dull. Okay, what is it that is additionally knitted by the presence of tokens that makes it definitively not dull?
Because it separates out what's being ingested versus what's actually a spectator in a way that isn't separated out in a global multi-way system. Okay,
but is it obvious? I mean, if we pick a different, I'm sure I looked at this. I mean, I certainly, back in those days, I was in a very enumerative mood, and I'm sure I tried every possible rule of a certain type for its causal branch hill graph. But is there an obvious reason? Let's see. Can you reason through why the causal branch hill graph is usually boring?
No, I mean, I never claimed that I knew that it was. It's just that in all the examples I've seen, the structure is rather trivial. I think global multi-way systems make it a lot clearer that it's not trivial.
Okay, all right, okay, so let's understand that. So you're saying, so if I were to just lift out here, but I don't understand, why is the brown connectivity or the orange connectivity any different from the connectivity that you just showed me of the causal branch hill graph?
So it occurs because the way we assess causal structure in the global multi-way system only looks at the sort of the live tokens rather than the spectator tokens.
Okay, let's go through that. That's a tricky issue in all of our setups. And in fact, when I was looking at this multi-way systems based on numbers thing, numbers as such encode nothing. You have a 14. It doesn't really have a notion of the part of the 14 that gets acted on and the part that's a spectator. It's just the whole 14. What's that?
You have prime factorization.
Depending on what your operation is, yes. Yes, I mean, actually, the thing I was looking at, this multiplication thingy, actually, that's a fair observation that I could probably draw the causal graph based on factors.
I mean, I had a version of that when I first produced the multi-way function system function. I had a version of it that did exactly that, and I think you thought it was too esoteric, so we took it out.
Yes, I thought it was very weird. I mean, because it depends on the dynamics, whether factorization has any natural character to it. I mean, you could as well say, consider the number in unary, for example, and do it with addition.
Sure.
Okay, in any case, so in this case here, explain, so you're saying that, let's see, what are you saying? You're saying that these things are considered causally connected. You're saying that spectators can lead to causal connection. So for example, the identity event could lead to causal connection. A sequence of identity events could be causally connected in the traditional global causal graph story. And you're saying that's not true here.
Right. So if we take something like this, sorry, really trivial example, but makes the point. Mm-hmm. So the A's that are ingested by this event, those are spectator A's. But the fact that
Which
they are
ones? The A's on the two sides of the axis.
A's that are ingested.
Sorry?
The two A's that are ingested.
Yes.
But you can't really see that they're spectator A's until you break everything apart into tokens. And then you see, oh, actually these tokens, these two tokens were unchanged.
Yes.
And so the point is that the causal structure is the notion of causal precedence works slightly differently for a global multi-way system to a
okay, so put it a different way. If you think of the world in terms of tokens, it's easy to tell what changed and what didn't. If you think of the world in terms of complete states, you say the state changed, even though actually most of the state didn't change. Whereas here, what you're doing is you're accounting for change in a more fine-grained way.
Mm-hmm. Exactly.
Okay, I get it. So yeah, I mean, I've wondered about this thing about spectators and their involvement in causal connection. So this is homing in on the question of, is a spectator part of a causal connection? And it's basically saying you have a setup where spectators are not, where just hanging around isn't enough to have an effect, so to speak.
Exactly. Just being touched by the event isn't enough.
You have to be changed by the event. Now, what happens? So in other words, if it was the case that it was AXXA and it turned into AXYA, only the Y would be considered to be
that's correct. Yeah.
A genuine effect.
Yes.
Yeah, it's nice. Okay. I mean, I agree that that's one of many horrifying kind of, did it change what counts as equivalent type things? All right. So I get it. So now so if you lift that causal graph out of the full, if you lift the causal branchial graph out, what do you get?
Then you get I don't actually have code that does this, although it's quite easy to write. Then you'd get the global version of this thing here.
Exactly.
But it would have a lot more structure than this thing here.
Well, can we see it?
Yes, we can probably.
Those edges must be tagged. Surely you can just select edges from that.
The edges are not tagged, I'm afraid. Well, they're tagged with rendering, I guess.
That is disgusting.
What we could do is, okay, let me figure out how I'm going to do this. So, oh no, wait, this should be quite easy because I can just say.
You just select the edges that have events on the ends.
Wait.
Yes, that's right. Doesn't matter, either one of them. Yeah.
No, because you don't want the token to event things as well.
Okay, fine.
I think that would work, and then we just say, nope, that, hang on.
Let's see, can you make that bigger? Just let's see what it got.
Wait. Yeah.
Okay, there we go. Ooh, interesting. Oh, okay. Let's see that for, okay, can we see that after a few more time steps?
Yep.
Okay, why don't you just write a little wrapper function that extracts that from, well, it doesn't really matter. You want to get rid of the rules. You want to put the explicit rules in there.
Oh, sure. Yeah. Sorry. Yeah. About that.
Okay. Let's see that.
Do we really want the event rendering, or
not really? No. Why don't we just do structure? Okay.
We go to 7. Can we push it that far?
Let's try a trivial thing that has some kind of grid. What did this? Oh, lovely. Okay, do a graph 3D of that.
Just graph plot 3D.
Oh no, just say graph 3D. You don't need the plot. And now just make it bigger and wiggle it around. Unhelpful, but amusing. Okay.
It looks like it could be some part of a polymer or something.
I thought it was very, very summary based on its colors. But anyway.
Yes.
It looks like the kind of thing one might be allergic to if it was in some kind of anyway, never mind. Okay, let's go back. Can we try a more trivial rule and look at the corresponding?
I mean, unfortunately this is a pretty trivial rule.
A goes to AB. Oh my gosh. What happens if it's A goes to AA? Does that do nothing because of its
no, but that'll do something pretty similar, I think. I mean, look, I mean, we can make this a bit. Well,
I mean, there's just 3 steps of that. What that was a complete graph, basically, right?
Yeah,
no, that isn't a complete graph.
If we deduplicate tokens, we can make it simpler, but it'll lose a lot of interesting structure.
Well, let's look at it with deduplicated tokens.
Okay. Well, I mean, if I show the A goes to AB case, this will now be much higher connectivity.
Let me understand that. So the reason for that is that there are events that got connected because their tokens were considered equivalent. And so the events became related by virtue of the observer equivalencing equivalencing tokens.
Right, exactly.
So this is the implied observer equivalence version of this thing. Huh. Okay. So what this is basically saying is, if we thought about this in space-time, if you say all pieces of space are equivalent, then anything that happens anywhere is connected.
Mm-hmm.
And that's why all these events get connected, by virtue of the identification of different parts of space, basically.
Right.
Whereas if the different parts of space, it isn't quite the level of atoms of space, but if the different sort of fragments of space were completely separate, then the things that happen to them are happening separately.
Mm-hmm.
But why is there such an asymmetric? Okay, so for A goes to AB, could you show A goes to AB in a single A and don't deduplicate the tokens? Okay, why is that null?
Wait, maybe for an even number. Okay, hang on. Let's have a look. Yeah, that's pretty dull.
Okay, so what is that? What is that? What is that? Hold on.
No, because we were extracting the causal branch graph, and there's only ever going to be one event at each step. That's why it's dull.
I see. So it has to be thickened up.
Because look, that's what it looks like.
All right. Okay. So we might need a rule that has a bit more. What is the rule? Let's see. A goes to AB normally in the global multiway graph that produces a grid, correct?
For an AA initial condition, yeah, not for an A initial condition.
Ah.
For an A initial condition, it produces a path.
Yeah. Okay. Fine. Fine. So this is really doing something perfectly consistent with that.
Yep.
Okay, fine. Yeah, this is a slightly cheap way to get a two-dimensional thing, but yes. Okay, so what you're saying is, okay, but the main thing here, okay, so there's a carrier of I don't know what the heck this causal graph is. What do we call this causal graph? This is a sort of a token connected causal graph. What is the right term for it? It's a token-based causal graph as opposed to a state-based causal graph. It's a token causality-based causal graph. Token-wise causality versus state-wise causality. As in, it tracks only its way of deciding what affects what is what had tokens changed, as opposed to what had states changed.
Mm-hmm.
Okay, so what does this tell one about? Okay, so if we're thinking about space-time versus branch time, basically, what this is doing is, if this was a hypergraph-based system, then the tokens, do you have one of those?
Yep, let's load her up.
Oh, well, that's very exciting.
Okay. Here's one. The problem is this code is super slow. This is the reason I haven't submitted it to the function repository yet, is I'm still working on optimizing it. But okay, let's do maybe one step. Oh yeah, sorry, it's going to have to pull in the...
Okay, but I mean, basically what's going to happen here... Oh, gosh. Okay, it's more useful, I think, to see at a conceptual level. So what's going to happen is the tokens are now hyperedges. The deduplication of hyperedges is isomorphism of hyperedges, right?
Yep. Here's the
Wait a minute. That's a very, very weird thing to do, because in actual space, those hyperedges contain different atoms of space. all the hyperedges in the universe, they are knitted together by their common atoms of space. But many hyperedges have, hyperedges on two opposite sides of the universe typically have completely distinct atoms of space in them.
Yep.
So when you deduplicate all the hyperedges, you're saying that even though it's, the hyperedge is in some quasar at the other side of the universe, I'm going to consider it because it has the same structural form as a local hyperedge. I'm going to consider it, I'm going to ignore the labels. I'm going to ignore the knitting of those hyperedges together. I'm just going to conflate them all, correct?
Right. I mean, it's corresponding to the fact that branch-like locality is not the same as space-like locality. So it's entirely consistent with the branchial causal structure for you to have hyperedges that lie on opposite sides of the universe being ingested into the same event, so long as they match the pattern.
Right. But that's saying, I mean, that's the question of whether, whether entanglement, whether the speed of entanglement in physical space is infinite or not.
Mm-hmm.
And this is saying, if you can, it's just as well that nobody has decided, there are all these things you can't do on, these days, you can't smoke a cigar or something. It's just as well that nobody's decided you can't eat whatever we're eating. Never mind.
I'm sorry, I didn't realize.
No. I did that too, and it's for me it's necessary because the alternative is either the glucose supply to the brain, dies off if I don't eat a piece of chocolate or something, and then no multiway systems come out. Anyway, but so the point that you're making is, okay, so is that without deduplication?
No, that's with deduplication. Without would be kind of, deduplicate. This is going to be
a horrible mess.
It will be, actually, maybe I can make it a bit faster if we don't do the rendering. But yeah, it'll be something like that.
Okay. All right.
The rendering is definitely the bottleneck with Wolfram model systems.
Okay, so hold on. Let me just think about what this means. What you're saying is, on two branches of history, okay, in general, the version of space that is generated on two different branches of history will be connected by the common ancestry of those branches, in the sense that there may be two atoms of space that exist on those two branches of history, which are the same atom of space, because they both came from the same event, but they were on different sides of a branch pair.
Right.
And then what you're saying is that one thing you can do is to say, I'm just going to conflate I'm just going to ignore every label on every atom of space. And I'm going to put them all together. And that's what token deduplication is doing here. Is that right?
That is correct, yeah.
What on earth is the physical interpretation of that? I mean, it's basically saying all of space, we're ignoring space. We're ignoring the fact that there is extent to space.
Right. Well, you only care about branchial locality. You don't care about space-like locality.
Right, which is the story of quantum mechanics, if not quantum field theory.
Right. Right. Quite.
But so, okay. But now, for example, in that picture there, you seem to have two hyperedges down at the bottom there, the figure 8 things, which look, maybe they're not the same. Maybe they have different arrow structure.
I think they must have different arrow structure.
Okay, fine. Now, I mean, we could imagine a generalization of this, where instead of deduplicating, I mean, maybe this is too ornate, instead of deduplicating as we progressively try and approximate genuine space-time, we could say, let us not deduplicate things just at the level of individual hyperedges, but let me look at subgraphs and deduplicate only across a subgraph.
Well, there's an intermediate. I agree. That's also useful, but there's also an intermediate case for the Wolfram model system that doesn't exist with these other systems, which is that you could have deduplication where you don't do isomorphism checking. You just merge, hyperedges as lists that are equivalent. If you get what I mean.
Yeah, I understand what you mean. Well, okay, if they're lists that are equivalent, then that means that the name of the atoms of space, the names of the atoms.
That's exactly the point. So then you have a notion of deduplication that preserves spatial structure. That's the reason.
Indeed. And what does that do? How much deduplication happens in that case? Is there significant deduplication?
Well, I haven't looked at it. I'm saying that seems like
right.
an intermediate.
I mean, so what that would successfully deduplicate is, that's a good idea, because what it will successfully deduplicate is things on different branches of history, which are just the same thing, basically.
Mm-hmm. Precisely.
Right. So in other words, an event that picks up a given collection of atoms, and there are multiple events. So for example, in the case where there are spectators, that will be a dramatic savings. If you included spectators, that will be a dramatic savings, because then you are conflating together. Well, it depends. I don't know. No, this is complicated. So, I mean, obviously, so I did a bunch of experiments with this in this whole multi-space idea. Did you do a Turing machine version of this?
Mm-hmm. Again, this is not very efficient, which is why I haven't put this in the function repository yet. But let's take an example. Here's a non-deterministic Turing machine.
Can rendering. You do a deterministic one, just so I understand what's going on? You just
okay. Sure. Very dull.
Okay, is that deduplicated?
No.
Okay, so the spectation, so to speak, whatever the right noun from that is, the reason this is quite weird is because the head, you are simply extracting the head independent of where it is and calling that the token.
Well, okay, so this is why I need to figure out a less dopey way of rendering it, right? Because the point is, these tokens are just positions on the tape. When you call rule plot Turing machine with a one, with a one place tape, it will plot the head at that position.
But you say you're really storing there the full state of the head and position of the head. Is that correct?
Yes. Yeah. It's just that there aren't, because of how it's being rendered, there isn't a place to put the head apart from in the one square where it can go, if you see what I'm saying. Yeah,
I understand. What you could do rendering wise is you could just ghost the rest of it. You could just have the framework of the rest of the tape.
No, sure. I need to write a less silly rendering function. But
okay, but basically each one of those. So at a given level, in a deterministic Turing machine, okay, I am totally confused here. In a deterministic Turing machine, why isn't there just one head configuration at every step?
There is. You can see the two head states are the same.
I mean, they're the same.
They're both pointing.
But why is it on a different color of tape?
What do you mean? The tape is 4 squares. 0, 1, 0, 0. So there are 2 white squares and 1 orange square being ingested into this event.
Oh, but wait a minute. But I see. But it is incorrect to put. I see. So the problem is in the rendering here. The fact that there is a head on that white square is not right for most of the white squares.
So it's showing the right head state, but it's not, the head is not located necessarily on this square.
Right, but isn't it the case? Why are these those deduplicated? Because aren't those white squares things which should be labeled by their position? Or are you not considering? I mean, in the isomorphism testing, the question is, do you account for position of the cell?
No, I mean, we don't do that in strings, for
Fair
instance.
enough.
So I don't see why we would in Turing machines.
That's really weird. So, I mean, a Turing machine, unlike a string, which is a finite length, a Turing machine is conceptually of infinite length. So at every step, there's an infinite number of blank tape cells, blank tape squares that should be being ingested.
Right, so you'd have infinitely many arrows coming into each event.
Right, so that gives a serious weight to the spectators. Like there are an infinite number of spectators.
Right.
So getting rid of spectators, but why? I see, for the purpose of the event. No, I'm just confused, totally confused again. In a global multiway system, the events still contain their spectators, yes?
Yes.
So the events contain the infinite blank tapes, right? But the tokens do not.
Mm-hmm.
Boy, this is slightly head spinning, not to think of Turing machine heads too much, which, okay, the question really, as far as I'm concerned, is one of the things that we would like to do is to get a good simultaneous representation of physical space and branchial space.
Mm-hmm.
Does this help us with that?
Well, I mean, that's why I was kind of excited about these local branchial graphs, right? Because everything about this physical spatial structure is reconstructible from the event ancestry, and everything about the branchial structure is reconstructible from the token ancestry. And then the coupling between the two comes from the edges that connect both.
All right, that's reasonably exciting. Yes. Okay, let me think about that for a second.
Because in effect, these are telling you space-like separations, right? They're telling you antichains, these orange edges.
Yeah.
One way you can think about them. And then these are telling you antichains in the branchial graph, the purple edges. And then there's mixtures between the two, which are also encoded.
All right, okay. Now I'm more excited. Okay. So you're saying that hanging around some of the spatial structure, there are little pieces of branchial froth, basically. That if we think of this thing having a backbone that's the spatial causal connections.
Mm-hmm. Right, this thing here.
Yes. But so what that's saying in the picture above is that there is no branchial connection between one side of space and the other. Is that right? At least there's no one-step branchial connection between one side of space and the other.
Right. There's an entanglement horizon here.
Well, but this is only recording one-step ancestry, right?
Right. So you need to see a hypergraph version of this, which would be a bit complicated. But.
Well, what would that hypergraph? So the hypergraph version would go back and, I mean, the hypergraph here would read backwards through a series of token event type a sequence, would it not?
Right.
So, and what would you expect to see there? So what you would expect to see, well, ultimately everything goes back to the Big Bang and everything is related to everything.
Right.
So what you're seeing here is some things are recently entangled, as in recently branchially related. And what you're seeing here is the mapping, but this is very nice. Okay, so you're seeing the mapping, the correspondence between what is spatially recently connected and what is branchially recently connected.
Mm-hmm.
Right? So the obvious question then is, this question of maximum entanglement speed, that which is to make a an EPR type setup, you need the way you would make that is you would have something where there's a branchial edge here that spans a lot of spatial, where instead of, if you want to get from here to there, you might go spatial edge, spatial edge, spatial edge to, tooling across the universe, so to speak. Or you might hop on one branchial edge. That a fair assessment? So the question then is, how local the spatial structure we believe to be local. So imagine that it made a manifold, for example. That would be a nice spatial manifold that would represent space. Then the question is, does the branchial structure that sits around that also inherit some kind of manifold type structure?
Right.
Because what we're seeing here is a pretty local branchial, froth. What happens if we go another couple of steps and don't show?
I was going to check. So
get rid of all the rendering.
Should we go to 6? Maybe 7.
All right, so what we're seeing here.
Is that too much? There we go.
Okay, let's admire this thing for a moment. Okay, so it has some branchial backbones.
This is the causal bit.
Right. So it's roughly some kind of one-dimensionally-ish thing spatially. And what you're seeing there, scroll back up to what the heck is that? Scroll back up to the thing.
Branchial stuff, which is a bit less exciting.
Okay, so what that's showing is, in that picture, it seems that the branchial edges are hanging off the spatial edges, in effect.
Right.
That is that there are very few highways. There are very few, wormholes where you can go. It is literally, it's what the heck is it? It's an ER equals EPR wormhole.
Something like that, yeah. For this particular system, the causal structure is kind of the spatial causal structure, if you like, is needed to kind of knit together the whole branchial graph. Otherwise, it would sort of fall apart.
I get that, right? I get that, but I mean, just to interpret this picture for a second, a wormhole in physical space would be assume that the causal structure forms a nice manifold. A wormhole in physical space would be a shortcut from one part of that manifold to another in the causal structure.
Yeah.
Right? Okay. An entanglement wormhole, so to speak, an EPR as opposed to an ER, would be a place where the branchial edges jump, sort of deliver you to tokens that are near events that were otherwise difficult to get to in space.
Right.
So in a sense, okay, so what would ER equals EPR mean in this context? It would basically mean you can as well, it's sort of equivalent to jump around in physical space. Well, it is rare to have a fast jump from one part of physical space to another, but you can do it. And it's rare to have a fast jump in branchial space, but you can do it.
I mean, at some level, one interpretation of the ER equals EPR conjecture is that it's saying that the coloring in the local branchial graph is
irrelevant.
Right.
Yeah.
It's saying that like from the point of view of causality and locality, it doesn't matter whether you're traversing a branchial edge or a causal edge.
Right. But what that's saying is that at a microscopic level, well, okay, so that's surprising, honestly. It's a bit surprising. Well, maybe it isn't surprising. Maybe it is the reason that quantum mechanics isn't in your face every day. Because basically, most of the time, spatial structure is enough to account for what's going on.
Right, right. And it's only in very extreme conditions that you'd need to actually have a separation between the two, or you need to enforce a separation between the two.
Let's understand that for a second. So what you're saying is a quantum effect in this picture would be something where there is a very separated branchial connection that is not achievable through spatial connections. I mean, that's what it would mean to have to
have non-locality and entanglement, for instance.
Yes. And so let's see, what would that look like? So that means that in a sense, you have to beat computational irreducibility. It can't look too random. It's got to have some systematic prong that connects one part to another.
Mm-hmm.
That's nice, though. I mean, that's a nice picture of the relationship between causal edges and branchial edges. But let's just go through this one more time. So what we would expect if we did this for a hypergraph system, the causal edges are genuine representations of, they account for the different names of atoms of space.
Yes.
You know, the problem with this is going to be, okay, but wait a minute, and this doesn't token deduplicate. So this hasn't forcibly crushed out space when it comes to the branchial direction, right?
Right. If we did that,
you get nothing. We just crush to nothing. So the interesting case is not deduplicating tokens.
Right.
But the advantage is we have a little bit less information about the branchial. What is the point here? So we're basically making equivalence classes. Yeah, I mean, what we're doing is we're crushing every complete spatial state and saying, just give me your tokens. Right, and then we're saying, how are your tokens connected? I don't care about how the rest of the spatial state is connected, I think.
Right.
Right interpretation. I want to try this one more time, explaining what this picture actually is. So each one of those blue nodes is a token. No, I don't understand this. I'm confused. Can we look again at one of those sort of space-time pictures before we get
You mean like one of these?
Yeah, one with labels. Okay, that's right. This is a branchial graph. So this is at a certain moment in time. This is showing ancestral connections between things. Okay, actually, here's the thing worth remembering. To reconstruct space from a causal graph, you can do that by a branchial construction. Right? So in other words, if you've given a causal graph, the structure of space in reality is reconstructed. The thing that is real is the causal graph, and you're reconstructing the structure of space by looking at essentially a branchial construction on the causal graph.
That's what this is
essentially what you're doing here.
It's not essentially what we're doing here. I mean, that's just how that's the definition of an antichain. That's how.
Defined relative, wait a minute, was this defined relative to tokens, or is this defined relative to other events?
This is defined relative to events.
Okay, so this is the true event-to-event spatial reconstruction. Is that right?
Yeah.
Okay. So that is a genuine spatial reconstruction. So then the stuff that's around it is
showing the evolution ancestry of the tokens that appear with that are generated by those events, that appear within those events.
right. So I think what this is showing is essentially the one-step quantum fluffing of space-time.
Well, in this case of space.
Yeah, space.
It's
rather.
taking a specification of a space-like hypersurface, and it's effectively telling you what ambiguities exist in the tokens as a consequence of the fact that that this system is quantum mechanical.
One-step quantum mechanical.
Right.
So in principle, one could do the same thing with a two-step, the two steps away tokens. And that would then show how space basically disintegrates at a quantum level.
Right. Which
That's
you'll see.
very interesting. Okay, so let's go on through this again. So basically the backbone is the instantaneous state of space, no, wait a minute. Now I'm confused by something. This is not the single instantaneous state of space because it allows many different histories to have been chosen, right?
Right.
So what actually is it? It's not the state of space. It's the state of what? Of all possible space or what?
Well, again, I never know what you mean when you just say space, right? This is showing the antichain structure of the causal graph, of the branchial causal graph, or the local causal graph.
But I understand, but the anti-chain structure of a causal graph with a single thread of history is a reconstruction of the instantaneous state of space.
But it's a reconstruction of like hypersurface on one branch of history. This would be the analog here. This is a reconstruction of the moduli space of space-like hypersurfaces.
Explain that. Okay, so you're saying why is it by moduli space, you mean the set of all possible ones knitted together, is that right?
Well, all possible at that for that particular time step and that particular rule, which is
yes, right. But I mean, but the fact is that
of possible space-like hypersurfaces with a topology defined on them, which forms a moduli space.
Okay, but if we were to pick a particular evaluation history, we would get a small part of this graph, right?
Yep. I mean, we can see that if we want.
Yeah, let's see it. Don't mess up what you've already got. It's beautiful.
Okay.
Don't destroy what you already have.
So, your favorite event selection function, or should we just do sequential? It's maximally boring. Yeah, we get something totally trivial. I mean, it's a string. What do you expect?
For what? That's okay. That's showing. Okay, that's a little bit confusing to me because that's saying that most of the spatial structure is multi-way spatial structure.
It's a string. Almost all of it will be.
Oh, that's right. There's a string. Oh boy. Okay, so in fact, we're a little bit confused here. In fact, that thing we were seeing was mostly not, in fact, ordinary spatial structure.
Again, I don't know what you mean when you say ordinary spatial structure. It's a graph of causal antichains, of local causal.
I understand that, but I mean, okay, we have at least the concept that we are currently embedded in ordinary space, where you are on one side of the Atlantic, I'm on the other side of the Atlantic. There's a definite notion of space. We do not have this idea of essentially a quantum space or a multi-way space. We imagine that we're living in a definite space.
Well, the single history space-like hypersurfaces for a string substitution system are always going to be trivial.
I understand that. I understand that. But I'm trying to understand that insofar as we are trying to map what we're seeing here onto our usual interpretation of space and quantum mechanics, I'm trying to understand how that works. And I agree that the model probably for hypergraph systems, this is going to be more, there might be structure here, even in the single history case, right? If this were a Wolfram model rule, there would be structure even in the single history case, or at least there could be, correct?
Yep. Mm-hmm.
And so then the plot that you made that was previously just that boring branchial graph could be a much puffier, more interesting thing full of causal edges.
Right.
That would represent a single branch of history.
Yep.
And which would show for that single branch of history what the kind of neighboring branches were based on genuine branchial edges. Is that correct? I think that's correct. You're showing the branchial sort of, you're showing the delta, I wouldn't say delta X, right? Because it's delta B. What you're showing here is where B is branchial direction. B is a branchial vector, so to speak. Branchial variable or something. Is that not correct? That what you're seeing here is sort of, in a sense, by showing the one-step branchial graph, you're showing delta B, plus minus, well, not really plus minus, but something like plus minus delta B. Is that the right interpretation?
I mean, in the sense that 1 is a possible value of a branch-like distance, which you could call delta B.
That's what I'm saying, yes.
Yes.
But I mean, in general, there can be much higher branch-like distances, but these are not showing that. This is just showing the local, this is just showing the neighborhood, the branchial neighborhood of this multi-spatial space-like structure. Is that a correct statement?
That is correct. All branchial graphs that we've investigated thus far have been one-step branchial graphs.
No, I understand that, but by using, in the spatial structure, it is a delta T, but not delta X. In ordinary spatial structure, in our interpretation of space, we're seeing, our vision of the universe is we see all of space at a particular time.
Yes. Well, in both cases, in both the branchial case and in the causal case, of course, the antichain structure is determined by considering what happens one time step back. So you're perturbing in T in order to obtain B or X.
Exactly.
That's how you assess the antichains. That's the same in space-time as it is in branchial space.
No, I realize that, but the fact that you're doing this, the fact that you've got this local setup with local tokens, individual tokens, means that there isn't a symmetry here between space and between causal space, so to speak, and branchial space. Right? The very fact that you're having global events, local tokens, means that your treatment of the branchial direction is different from your treatment of the spatial direction.
Well, only in the sense that the branchial direction has higher granularity. If you collapsed all tokens into single states, they would be identical. They would be compatible.
I mean, all tokens into single states. What do you mean? You have crushed down the states into their individual tokens.
Yeah. So every pair of tokens here can be collapsed into a single state in some global multi-way system. So there's always enough information present here to do that.
Okay, so what you're claiming is that this picture shown below still has the difference that the events don't account for spectator. If I'm not mistaken, the events ignore spectators, yes?
Yeah, but that doesn't imply that branchial directions and causal directions are non-commutative.
No, I agree. I agree. But what you're saying is you could draw a version of that picture that has those kinds of events, but where the states have been reconstructed. And instead of individual tokens there, you've just got a bunch of states floating around the events, correct?
Right, exactly.
That might be an interesting picture.
Right.
So that picture then is, it is a causal graph backboned version of what states are near what causal, what events. Yeah, that makes sense. Now I'm confused by something else. If there are two identical events on two different branches of history, how does this work? In a Wolfram model rule, those two events will be ingesting differently numbered atoms of space.
Right. So again, it depends on the deduplication semantics. So in this case, where there's no deduplication semantics, you can have equivalent events like this one and this one appearing on different branches of history and they don't get merged. If you did have a deduplication semantics, they might.
And the thing that's worth us remembering is, in a sense, deduplication semantics is a story of the observer. Ultimately, the observer is what does the deduplication. So in a sense, the universe, I don't think we have to say is deduplicating at all. It's just that we conflate all those identical branches, and that's how we build up synthesize our version of reality. Well, these are quite lovely. I mean, they're clearly, it's amazing. The number of different kinds of graphs that seem relevant is just absurdly great. And I wonder how we should think about that. What is this? Oh, wow. Oh, I got to see this one.
This is just me playing around with what would combinators look like in a global multi-way context.
Oh, my gosh. Okay, let me see if my brain can maintain integrity here. What's that?
So we have S, K, I, X, and Y as our initial tokens.
Why aren't you just using SK?
I mean, I can do.
Okay, fine. But it's going to matter, because if you just use S and K, at every...
Well, hang on, let me get some, let me find some examples.
And if you go to my post, you'll find, you can go there.
Let's try something like this.
Yeah, we have some comments on live stream. EVP is asking, what's the difference in observer and spectators? Okay, totally different things. The observer is us trying to parse what's happening in these systems and doing things like saying, those two hypergraphs are isomorphic, so to me, they just seem the same. That's one thing. The other thing is, in the low-level structure of these systems, is there something which is in this hypergraph and elements, atoms of space in the hypergraph, which is simply not affected by a given event? Let's see. There's comments here. Is the interpretation that branchial space is independent of the dimensions of causal space? Yes. Branchial space branchial space is probably exponential dimensional, as we expect from it being Hilbert space-like thing, as opposed to something finite dimensional like ordinary physical space. Duplication and branchial collisions. Boy. Yeah, Eli is commenting, the observer is preserving the identity of a rulial multiway system. Yeah, the observer in the rulial case is yet another level of mind-bending stuff, which I'm just trying to write about and untangle a bit, so I may be able to untangle it. This is saying, try only using S. Okay, what do we got here? We've got combinators doing that thing.
Oh no, sorry. These were the combinators I was showing. This is general like Wolfram model expression evaluation. So This is what group theory looks like when it's glocalized.
Okay, let me see if I understand this.
So we're defining axioms of group theory as just replacement rules.
So every event is the action of an axiom.
Yeah, so G being a composition operator. And then we're starting from the initial expression G of X comma Y and evolving it. And this is what we get.
Okay, so what this is doing effectively is this is applying valid axioms to get expressions which are equivalent to G of X, Y, correct?
The ordinary multi-way operator system, if you look at it like this is, at some level, you can just think of this as being, a proof of all theorems that
to GXY.
Yeah, that state an equivalence to GXY. So I was just curious of what would this look like? What, effectively, what would evaluation, what would pattern evaluation look like in the global multi-way case? And I don't know. It's kind
of... But so let's understand this picture. I mean, so in the first approximation, okay. So if you say any sequence of symbols, okay, you would get the free tree, so to speak, if any sequence of symbols was equivalent, correct?
Mm-hmm.
Okay. But so in that case, what you would see is every node of the tree, it would just branch out, and every node would be an event that just says add symbols to things. In this case, it's a more constrained setup. And I don't understand what this is doing. So every event is the application of an axiom.
Mm-hmm.
What is that?
It's the deduplicated version.
What's that?
It's the token deduplicated version.
What does that mean? I mean, usually if you take an individual combinator like an S and a K out of its natural habitat, it's pretty meaningless. Like an element of a string. I mean, a string, that is the big difference between the Wolfram Model rules, where the atoms of space have an identity, even if extracted from their environment, so to speak. Whereas the truth of a string system is that the characters in the string should be labeled by their position. Just as in a Turing machine, you say the head is at a certain position on the tape. Now, in the combinator case, it is more complicated because you have to label every S and K by its tree part number, I believe.
Yes. That's why the combinator and operator systems are treated like the internal workings are yet different again.
Okay, but when you do that, if you are deduplicating across all levels of the tree and across all part numbers, what the heck are you doing? I mean, it's just crushing.
That's the point. You're not deduplicating across all levels of the tree. You're only deduplicating at the same level of the tree. Hence why there are multiple G's here and multiple...
Why at the... Okay, wait a minute. That's just your choice of deduplication semantics, yes?
Yeah, sure. I mean, so actually, ultimately, I want to replace this deduplicate tokens option with something that, a bit like with event selection functions that has several built-in deduplication semantics.
Although in general, there's a question of is deduplication context independent? Because that's not, I mean, deduplication, okay, the most coarse deduplication just says if you're an X and there's another X, conflate them. Right? The next level up would say, if you're an X embedded in F of X, don't deduplicate relative to one embedded in G of X.
Right.
So in a sense, deduplication, what you need, I mean, it reminds me in some bizarre way of these things for doing, like XML editing and so on, where you depend on the, where instead of just saying, replace this with this, you say, if there is this set of parent elements in the tree, then do this, otherwise don't.
Right. Yeah, you basically, you need to know everything that's further above you in the tree in general.
In the combinator case, it's a tree because the actual representation of the thing itself is
Well, in both the operator case and the combinator case.
Right. The operator case is also expression trees.
Right.
But, okay, so you're doing bi-level deduplication.
Yeah.
Correct?
That's correct.
So in a sense, if I were to write out the expression trees, you are sliding. It's as if you have them on rails and you're sliding tokens around on those rails, but you're never crossing down to a different level of rail.
Yeah, exactly.
Oh my gosh. Just
So
imagine people in traditional pure mathematics trying to describe that operation.
So like here, you can see it directly, right? So there's a y here and there's a y here. Why are there two different y's? This y is contained inside the outer g, but not the inner g, whereas this y is contained inside the outer g and the inner g.
All right, just as a little exercise, if you were to describe this pure mathematically, you have at your disposal traditional pure mathematics, category theory, type theory. What on earth would you say to describe this? I mean, this is easy to describe in terms of symbolic operations, in terms of structural symbolic thinking, so to speak. Mm-hmm. But how would you describe something like this? This context dependent, in other words, you're making equivalence classes. What are they? Are they some level of some type hierarchy that's being, I don't know what the heck it is.
Is that a rhetorical question?
No, it was a question for you because I don't have any idea.
You just have a deduplication semantics that depends on the recursion history of each operand. The recursion depth and in more general.
Yes, I understand that. And if you're actually dealing with a symbolic language, that's a meaningful thing to do. But I'm asking the question, when you look at these things in type theory, there is a somewhat reasonable representation of these nested thingies.
Yep.
Fair statement?
Yep.
Whereas category theory doesn't really have much to say about these nested thingies. Is that a true statement?
I don't really understand what that means. I mean, type theory and category theory are different, completely
different.
No,
I'm asking, in type theory, it is fairly natural to talk about these recursive kinds of structures.
Yes.
But in category theory, I don't think that it is.
Why do you say that?
Well, what do they correspond to? I mean, in terms of when you recurse down like this.
I don't understand the statement. I mean, type theory is a model of computation. Yes. Category theory is not.
I understand that. Okay, fair enough. But the question that I'm asking is, if you were to try and describe what you just described as a piece of pure mathematics, so to speak, standard pure mathematics, non-symbolic structural pure mathematics, I'm just curious, what does pure mathematics, I mean, is there some, because these are things which are somewhat natural to discuss in a symbolic structural way. And I'm just wondering whether there's a way to get there from, does this connect to some version of, I don't know what, some kind of interpretation of set theory where you've got things inside things, and I don't know. That was what I was just curious about. Is there any obvious thing that this connects to? Or is it something that is not easily formulated in so these traditional pure mathematical terms?
I don't even understand the question. I mean, is it anything that involves a notion of recursion, you can express this idea in, right? So yeah, of course, set theory, class theory, type theory, all permit recursion.
Fair enough. Okay. I think I was making a point which has gone splat. I'm just trying to understand. In the case of group theory here, for example, I'm just struggling to understand. If you were thinking about this in terms of universal algebra, for example, is there an interpretation of this token granularized, oh boy, yeah, of the sort of token granularized version of algebra?
Sure. It corresponds to a different delooping operation on a loop space.
Ah, okay. This was the kind of thing I was fishing for. Okay, what is a loop space?
Well, they're the primary objects of study in universal algebra.
wait a minute. Universal algebra in the, maybe I'm 100 years out of date, but in the Whitehead version of universal algebra, what what one meant was just there are operators, they take some number of operands, and you are writing down expressions that involve just a symbolically specified operator, f, for example. And then you're discussing,
exactly,
for example,
what equational proof uses internally. It's what multi-way operator systems use. It's what our entire theorem proving stack uses.
Which, the thing I just described?
Well, equational logic is logic that describes universal algebraic theories.
Yes, I understand. But then what is a loop space?
Well, so a loop is the minimal case of a universal algebraic theory. It's the kind of fundamental object of study in universal algebra.
How is it defined?
Well, it's the algebraic structure that's defined by the equality predicate.
Oh, I see. Okay. I mean, I remember that there are axioms of loop theory, and which I never paid much attention to. But those are, what you're saying is, those are the axioms that describe function application and equality. Is that right?
Effectively, yeah. And then in the same construction that would give you a stone space for a Boolean algebra or Heiting algebra or something, there's an analogous procedure that lets you construct a topological space that preserves the structure of the loop, and that gives you a loop space. And then there's a way that you can so-called deloop that space, which gives you back to something axiomatic from this topological structure. And there are multiple ways of delooping. And I haven't proved it formally, but I'm pretty sure that these different representations of multi-way operator systems essentially correspond to different delooping operations.
Why is it called a loop space, by the way?
I don't know. There is some reason, but I've forgotten what it was.
Okay, fair enough. But I mean, when you talk about looping and delooping, and you talk about the space, so you've got this thing, we can represent it symbolically as, f of x's and y's, some operator f, and then variables x and y, and so on and so on and so on. What is the way that you make a space out of that?
Like I said, the same way that you do it for a stone space. You treat the symbolic operators as defining enclosure or containment relations between open sets, so you get a topology.
Oh, this is poking at the top of my reading level here. But I suspect it's closely related to the things you've been doing recently with toposes and so on, but we're not probably going to have time to get into that. But can you explain that for a second? So you're saying interpret the variables as open sets.
Well, no, so when you have, you have an equational theory. Well, actually, let's do an explicit example, right? You have an equational theory like this. This defines an order relation. Okay, it's complicated by the fact that you have these loops that appear here, but there's a way you can.
Nothing to do with loop spaces. They're just loops.
Yes, I believe they have nothing to do with loop spaces, but
who's to know? Okay,
you could get rid of them. So in effect, what you're saying is we've got some collection of expressions, and they're partially ordered by this operation.
Yep.
Right. And so that gives, so now interpret each one of those expressions as an open set. And we define a rule that says one open set is contained in another if the corresponding expression appears below the other one in this partial order.
Okay.
So if you do this for the case of a Boolean algebra, you get a particular kind of topological space, a stone space. If you do this for the case of a general kind of universal algebraic theory, you get a loop space.
So, but by the way, the stone thing, what is it, the stone representation theorem or something, whose main consequences that I know are rather straightforward facts about, models of Boolean algebra being only 2 to the n sized and things like that. But if you did this for a Boolean algebra, what does this picture look like for Boolean algebra?
We can find out.
Yeah, why don't we find out?
I think I might have put Boolean algebra as an example in multi-way operator systems documentation, but I can't remember. If I was clever, I would have put it in examples, but I didn't. Okay, but that's all right. We can.
You just have to have an equivalent. I mean, you just have to have the the relations. I mean, otherwise you're just nanding everything together, and then you're reducing it by certain relations. I think that's an overly complicated. I would recommend using my pure NAND one. Wouldn't that be easier? Yeah, I think that's easier. Maybe you want to use, if you want it to combine a bit more, I would recommend you use the one which has the version of those axioms of mine that has commutativity as well. Commutative axioms, yeah, that seems promising.
Oh gosh.
Well, okay, if it's more difficult if you have multiple relations, just use one relation.
No, it's fine. I was trying to work out, is there an easy way I can do this programmatically? But there probably is, but I can't be bothered.
Yeah.
Oh wait, no, I need formal symbols. This would have been a lot easier. I need to generate some variables.
Why do you need the unique? Why don't you just have it hang out of the module?
Oh, I guess you could, couldn't you? It would generate
just forget the uniques. Just have them be module variables. They're unique.
Yeah. Fair point. Okay, well, now let me try that to begin with. Wait.
Yeah.
This is going to get ugly, I suspect. But I don't know. What should we use? B dot C. Well,
yeah, you can have A dot B. I mean, and that should, or B dot C, X dot Y, whatever you want to use.
Let me just check that works. Okay, yes.
Yeah, and it's going to look like the free graph for a long time. In fact, it might look like the free graph for 100 steps.
Right, because the shortest non-trivial proof in your axiom system is long.
That's, by the way, an interesting fact in its own right. That okay, so let me understand what this is doing. So this is applying the axioms to make equivalence expressions. And now you're claiming, so what does the whole Stone business say about this? What does it tell you about this?
Suppose now that we didn't have a two-way version of this, suppose it was just a one-way implicative thing.
Yeah.
Then we have some DAG, and that DAG gives us an order relation.
Yep.
And so what you could do is just say, let's associate every expression with an open set. And let's say that one open set is contained in another, if and only if the corresponding expressions precede each other. So then the whole DAG defines the open set structure of some topological space.
Yep.
And that's a Stone space.
And what happens in that space?
Well, then it allows you to translate, these algebraic questions about Boolean algebra into topological questions about this space and
yeah, but what can you say about that space?
I don't know.
Okay. And I mean the loop spaces, what can you say about them? I mean, do they have any known sort of topological features and things?
They certainly do, and they become. But I'm not an expert on this particular area. I know that it becomes. The only thing I know is that it becomes relevant. So whether you have a Boolean algebra or a Heiting algebra, changes. Well, for obvious reasons, I guess it changes the distributivity properties of the topology of the space you construct, and I think the same is true with loop spaces.
What is the distributivity of topology?
Well, no. So the distributive law that you end up with for a Heiting algebra gives you effectively a distributive law for open sets in the corresponding space.
What is the distributive law for open sets? Distributive for what? Intersection and union or what?
Yeah.
Okay. So a distributive law of the underlying algebra implies, and with the definition you've given, that's not surprising, implies a distributive law for intersection and union.
Right. Right. And so then it becomes relevant, as I say, whether you're doing a constructive or a non-constructive logic as to, whether you have a Boolean algebra or a Heiting algebra. And so you end up with spaces which have slightly different, where intersections and unions behave, finite intersections and finite unions behave differently.
Right. All right, we probably are coming to the end of our time here. And what we got through, like, some fraction of a topic and a topic here. So we had at least two other really interesting topics that maybe we can cover another time.
Right.
And
I did just want to say, like, there are various reasons for wanting to investigate these local multiway systems. Wanting to understand the relationship between space-like hypersurface structure and branchial space structure is one of them. But another thing that I'm kind of taken with, and the reason I was looking at these combinators and operator system things, is I kind of want to know what would a theorem prover look like if it didn't have if it didn't use global states. So the implications that are used in the proof are global, but the actual specifications of the intermediate steps are tokenized. That's something I kind of wanted to experiment with at some point.
Well, and in fact, segues to a comment on a live stream from Bob saying that tree needs pruning. Yeah, you need a theorem prover. The theorem prover just, eventually is going to go down a single path in that tree. Although I don't know, is there a visualization of the operation of the theorem prover that shows what alternative paths it is considering?
I mean, we could construct one that wouldn't, but that's not actually how the theorem prover works. It's not searching paths systematically.
I know, it's doing this completion thing.
But in principle, we could do that, as a sort of pedagogical thing, we could show that. Right,
but the issue is here.
Sorry,
when you say, go ahead.
Just to explain why I think that's exciting. So suppose that you have some big complicated expression, that has lots of nesting of G's and things in it, for instance. And somewhere inside that expression, you end up proving, you have two expressions and they're basically the same, but inside one, deep nested inside one of them, there's a GXY, and deep nested inside the other, there's a GY. And you prove they're the same. Now, in an ordinary theorem prover, that wouldn't constitute a proof that GXY equals GYX, but for a global one, it would. So it lets you, so the class of lemmas that you can extract from a proof of a given size is, I worked out, should be exponentially larger for a local theorem prover than it would be for a global one.
Okay, let me paraphrase that statement. Okay, so for combinators, for example, you've got giant combinator trees. In the normal way of representing a combinator tree, even if there are identical subtrees, they're not, those common subexpressions are not unified, so to speak. And in the same way, you're saying, if you can prove some result about a deeply nested tree, it is not useful unless you are only proving results based on the root of the tree.
Right.
And so the question is tree-like separation, which I think have not been a big fan of, but anyway, I still like the concept of tree-like separation of things which are, different levels of nesting, so to speak, in the tree. The question is, it is a fact about algebra that things are, in some sense, homogeneous with respect to tree-like separation. Just like if we've got a list and there is two A's at different places in the list, those A's are considered the same. What you're commenting on is that a thing that's f of subtree is the same independent of what those subtrees, there can be relations about that, like f of subtree x, subtree y being the same as f of subtree y, subtree x, could be the same independent of what those subtrees are and where that appears.
Right. Actually, and so in a sense, ordinary theorem provers are using basically a multi-way operator system structure, which doesn't exploit this tree-like homogeneity, right? Whereas if you had a global theorem prover, you could just say, well, let me take one G token, one X token, one Y token, and prove something about this one G token, this one X token, this one Y token, and ignore everything else. And that would be a valid. Sorry?
Let me understand that, because isn't it the case that the downward tree is still covered? That is, the thing I just described just by virtue of variables, f of x, y equals f of y, x, those variables, x and y, can be arbitrary trees. What's not covered is that that f of x, y could itself appear as a sub-element of another tree.
No, exactly. It's where the case I'm talking about is the case where the theorem you want to prove is an equivalence between deeply nested subtrees.
Right. So in a sense, hacks like paramodulation, all those kinds of things, are ways of extracting little pieces of expressions and gluing them together in different ways. And what I think you might be getting towards is a generalization of of those hacks.
Something like that, yeah.
Right, because I mean, what you're saying is, instead of those hacks, take pieces of expressions and say how to sort of grind them up and combine them and so on. But what you're saying is, if I've got two trees and I want to, the question is, how does one tree read on another tree? And it could read by saying, you go down to a subtree to look at how this tree applies to that tree. Yeah, I claim what you've got is which would be very nice, because I mean, right now in theorem proving technology, there are, I don't even know, does our theorem prover use any of this paramodulation stuff?
Yes, it uses, so paramodulation is the thing that allows you to effectively interconvert between equalities and pattern rules internally.
Isn't that something like what we're talking about here?
Yes. Yeah, this is a generalized version of that.
Okay, fine. All right.
But as you kind of pointed out, it's a version of that, of like rule orientation or paramodulation, but which applies to subtrees as in addition to just whole trees.
This seems like a very interesting idea, Jonathan. I mean, it seems like something where, I mean, in the history of theorem proving, like people invented these things in the 1970s and 80s and things, these various kinds of grind up expression hackery type things. Yeah, well, so then what's mounting here is a collection of kind of more principled approaches to theorem proving. There's what you're developing basically. And this is one. You've also got the energy heuristic. Have you used the energy heuristic yet?
It depends what you mean by, I mean, we used it in a bunch of the ZX calculus stuff. I mean, that's the closest to it being used in anger, as far as I know.
Right, but like, there's no version of find equational proof that uses the energy heuristic.
No, I've been meaning to put one into the function repository at some point.
Is it easy to do?
Should be. Yeah, should be.
Don't you have to get into the insides of the theorem prover to be able to do it?
No, because so there's okay, so without wanting to go too into the weeds, internally we use there's a call to this Waldmeister C code that we use for doing fast. There are two things we use it for: doing fast confluence checking and fast critical pair analysis. And so we can call critical pair analysis basically on demand. And so all I have to do is just modify the way that, rather than calling that function repeatedly, we only call it when the energy heuristic says that we should call it. It doesn't actually require any modification of the backend C code. It just changes how
So it's a choice of what the ranking of what counts as a plausible critical pair to try is.
Right, exactly. So the ordinary approach is some kind of greedy algorithm where you just say, give me all the critical pairs and I'll resolve all of them and I'll keep going until we reach confluence. Here, what we want to do is say, give me some critical pairs and I'll only resolve the ones which lie on branches that have high causal connectivity.
Right, but I mean, the usual, whatever, unfailing completion type thing involves doing all of the critical pairs, right?
Yes.
And so this is in part a ranking. So in a sense, it's a ranking algorithm for critical pairs that prioritizes some over others. And like in Grosvenor bases, there's all these crazy things like, reverse lexicographic degree order, et cetera, et cetera, et cetera. And this is there an analog of that in the theorem proving world?
Well, yeah, I mean, so there are people, I mean, as you well know, the Buchberger's algorithm for Grosvenor basis reduction and the Knuth-Bendix completion algorithm are the same. They're both instances of this more general scheme. And so the same reverse lexicographic orderings that work for Grosvenor basis reduction in Buchberger's algorithm, you can also apply for Knuth-Bendix completion. But at some level, these orderings of effectively what deductions to apply when are a little bit arbitrary, and what we're trying to devise is one which is not so arbitrary, where there
right,
is
but I mean, in a sense, it's the same heuristic as the subdivide space when space has higher curvature, because that is what makes the curvature. It's as a way to do PDEs. This is the analog of that essentially in branchial space.
Yeah, it's adaptive mesh refinement for theorems.
Exactly, yes. But otherwise thought of as just as one of them is adaptive mesh refinement in physical space, is adaptive mesh refinement in branchial space.
Right.
Something like that. It's interesting. But so that's one meta approach. Then you're dealing with the fact that the entities in theorem proving are tree-like rather than being list-like, so to speak.
Mm-hmm.
And then the third thing is this proof-to-proof transformation stuff that you've been talking about.
Yeah, right. That's less well developed. I need to invest more time in that because it is interesting.
I mean, but so the concept there is just as the state of just as an expression is a symbolic thing on which you can do transformations, so is a proof.
Right. So if I take
It should work, shouldn't it? Oh, okay.
If I take
we need to add some more notable theorems. I'm going to make a note of suggesting that as a project.
Well, I mean, the problem I had, so I think all these are ones that I added. The problem is that it's quite hard to find universal algebraic theorems, if you see what I mean. Like,
no, I understand. For
theorems about particular groups are very common, but theorems about groups in general are kind of rare. Anyway, so the underlying idea is that like a proof graph is, it's some combinatorial structure, a bit like a ZX diagram or a bit like a generalized, tagged Wolfram model system, onto which you can then apply replacement operations.
Yep.
So there are things like, if you have two substitution lemmas and they're adjacent, we can merge them, because essentially by applying Genson's cut elimination lemma in reverse. Similarly, if there's a substitution lemma and then we can split it into, there are cases in which we can split it into two by applying Genson's cut elimination lemma. And there are similar things we can do, like if you have a critical pair and it has two ancestors, then you can, there are cases in which you can merge the ancestors and things like that. So there's a collection of purely combinatorial rules that you can apply to these proof graphs that give you equivalent proofs of the same proposition. And the idea is to do theorem, so you can construct a multi-way system of that. And then the idea is to do theorem proving on that multi-way system. So you're proving equivalences between proofs. And this gives you ways of doing sort of.
Right, but the question of, the thing which is interesting, which is not done by traditional theorem provers, is the go to the simplest one. That is, to given two proofs, what you're saying is you may have a way to establish the path between those proofs.
Right.
And it will be already interesting to look at how far is it between two proofs, because you might very well find that there are distinct proofs that have a sort of big topological hole in the space and proof space in between those proofs. And you might detect that by seeing that it's a long way from this proof to that proof.
Right. And in effect, that would be telling us that that the higher inductive type has, if we take its homotopic interpretation, that the corresponding type space has a non-trivial genus.
Yes.
We'd be directly probing.
Right, which is something that homotopy type theory has not been able to look at, right?
Well, certainly not concretely.
Do they know even theoretically what genuses of types of those things are like?
Yeah, people have constructed higher inductive types whose spaces have non-trivial genus, but they're very artificial constructions. They're certainly not the kinds of things you would expect to see in actual meta mathematics. But
right.
We can.
Look, the main thing that I think is interesting is this notion of destructive interference between proofs. That is, you've got two proofs where at an intermediate stage they are utterly incompatible.
Yeah.
Which I think is the analog of photons go through two slits. And I'm not quite sure it's similar to that type of situation, I think.
Yeah,
But
there's some kind of branchial event horizon.
yes, but I mean, but that's one thing, is to understand the structure of proof space, which seems highly interesting to me. The other thing would be to actually take a proof and simplify it. I mean, Noel McGill has been trying to take my Boolean algebra thing, automatically generated proof. I think he's gotten it down by some 20, 30% or something by I think essentially by hand feeding certain, guiding a theorem prover about what to do. But the question would be, is there a principal way? I mean, it reminds me a lot of things like compressing neural nets and things like this, where you're basically asking the question, can you make an equivalent, or program simplification? I mean, okay, to be fair, we have never succeeded in doing program simplification. We've tried it for decades, and we've never really got very far with it. Actually, it makes me wonder. I mean, we have got a whole bunch of rules for program simplification. Have we ever tried running those? I guess we don't have a simplify based on find equational proof. What would that look like? I mean, find equational proof just says, is it all equivalent to true?
Well, so this is what we did. This is precisely what we did for the ZX calculus case, right? This is how the circuit simplifier works. And the idea here would be to apply the same, exactly the same code, but for proof graphs rather than for ZX diagrams.
Is it using gradient descent, or is it doing something more fancy?
It's not using gradient descent. No, it's not using anything really apart from this causal edge heuristic.
But it must pick a way down, a way to get smaller.
I mean, okay, in that sense, it's using gradient. It's picking the one that it's picking whatever minimizes the vertex count. Yeah.
Right, but that's not obviously correct. I mean, it might be the case that you have to go over a hill to get down the hill.
Well, sure, yeah, you can always get stuck in local minima.
Right, but so that's a different issue. But it could very well be that you can get a long way just by essentially following gradient descent in this proof space, in this proof simplification space. I mean, there's no evidence. Is there any evidence? Okay. In fact, the very thing we've just been talking about the homotopic structure of proof space, is going to tell you whether gradient descent is going to work. Because if proof space is very uniform and there aren't any big holes in it and things, then you can expect that gradient descent stands a chance. If the thing is full of holes, then gradient descent is going to get stuck.
Well, the homology of the space is only one case in which gradient descent could fail, right? We also don't know anything about the geometry.
That's true.
That's partly the investigation.
Right. But on the other hand, by studying proof-to-proof transformations, we could reconstruct a geometry as well.
Absolutely.
I mean, in a sense, what you would be doing then is to make a graph in which every node of the graph is a proof. And you can say, so for example, you have a branchial proof graph, so to speak. I don't know, is it a branchial? I'm not sure what it is. It's a nearest neighbor proof graph. Given a space of proofs, you can look at which proofs are, what are the neighboring proofs in proof space based on these transformations, I would think.
Yep.
Yeah, that would be interesting to know. And what's your guess about the structure of that space? What kind of a space is it?
I await data. I don't know. I'm curious to know just how dependent it is on the underlying theory. My instinct,
bet it doesn't give a damn about the underlying theory.
But
I bet all it cares about is, if it cares about anything, it cares about things about the way that substitution lemmas combine and things like that.
Yeah.
I mean, because so far, if we look at our proof graphs, can you pick what was that one? That's a group theory? I don't have a clue that that's group theory. Can you identify, looking at the proof graph, can you say anything about what the underlying theory is?
So you can infer some things by how many critical pair lemmas there are, because there are some theories that are closer to confluence than others. But apart from that, I have no way of telling.
Right, which are closer to decidability, effectively.
Yeah. Well, I mean, they're all, yeah, I guess that's one way to think about it.
Right. I have to disappear because we've actually got another live stream about a completely different topic coming up in about 15 minutes. Well, very interesting. Don't forget to save that notebook, Jonathan.
Oh yeah,
We should put it in our collection. What do you want to call it? Global multiway -01 or something?
I shall add it to the archive.
Yeah, please. Very interesting. Look forward to seeing all those functions somewhere. Okay, we'll see everybody at another time.